Hello, welcome to another lesson. So today we're going to do the mechanics topic in extension 2, more specifically the projectile motions with resistance component of that topic. So it's a new topic to the new syllabus, where previously resisted motion was only on the vertical movement or the horizontal movement, never sort of in a projectile sort of motion. So it's new and exciting, and just comparing that to the extension 1 projectile motion topic. So in extension 1, there is no resistance that's in relation to air resistance, etc. There is only gravity. So it's quite different, and especially on the algebra integration side. So let me just share a screen and we'll get started. So, all right, so I guess a very good starting point for all of this is obviously projectile motion in extension 1, whereby you have only gravity as which influences acceleration on the vertical, and there is no horizontal acceleration, so without resistance. So if anything, it sort of acts as a source of comparison to the formula that we're going to derive. So I'm a diagrammatic person, so when we talk about projectiles without resistance, it sort of creates a nice little parabolic shape. So if I project an object at u meters per second at an angle against the horizontal of theta, we have 6 equations of motion, 3 for horizontal and 3 for vertical. So in the interest of time, just like one of those good cooking shows, I've prepared the formulas in advance. So these are the classic formulas you see. And what's important to note here, you can see there that the acceleration on the horizontal and acceleration on the vertical has no resistance. It's your classic 0 on the horizontal, which gives constant velocity horizontally, and only gravity impacting the forces on the horizontal, on the vertical. So quite simple, quite straightforward, and we've done that before in extension 1. So how do these formulas change? So what I'm going to do is that, and this might take, I guess, most of the video, and that's for me to derive and prove the formulae that we're going to use with resistance. So I guess now would be a good time to sort of outline that I'm going to make 3 videos. I like sort of the groups of 3s, and I've been doing those with the previous videos in mind. So the 3 videos I'm going to do, this first video, I'm going to do projectile motion with resistance, where the resistance is proportional to velocity. The next video, I'm going to do proportional to velocity squared. And the last video, I'll just do some sort of past paper questions and some other questions which you can see. So it's interesting because those 2 categories with proportional to velocity and then proportional to velocity squared appear to be the 2 buckets of questions that you'll see. And it's certainly the way that the Fitzpatrick textbook has sort of split the questions as well. So interestingly, Cambridge is currently silent on this topic. So I guess they're planning to then populate the topic with questions, probably in an updated copy of the textbook. So with resistance, what happens is you can imagine there is a force, right, on the horizontal, which acts against motion. So if your motion is going from left to right, the resistance is sort of coming against you. While vertically, if you're going up, the resistance is always going against you, so it comes down, and then when the ball or the object is dropping, the resistance coming against you going upwards. So I'm going to write the resistance for the y value, or the vertical going up and down, so because you don't know which way it is. And obviously also acting on this is you got gravity sort of acting downwards at all times. So what happens to the shape then, you can imagine that if it was a nice little parabola to begin with, it won't be a parabola anymore. It will probably be like some sort of shortened shape, which due to resistance sort of forces it down. So the horizontal total range traveled would be definitely less than the one without resistance. So once again, let's initiate this projectile at u meters per second at an angle of inclination of theta. So pardon me, the formulas that are basically proved, that we will need to prove, looks a little bit more complicated and looks like that. So the pertinent things here, and I'll prove it in the next slide onwards, is the starting point, which in effect is given, is we're going to start, and maybe I'll put a little subheading. Sorry, bear with me. I'm just going to move this down because I guess next video I'll do the second part of it. But for this first video, let's say resistance is proportional to velocity. Right, and that is key because when I do part 2 next video, all these formulas would just have a little square here, and that would be the difference. Now, for those that know their stuff, basically by having the square in there, what it does change is the integration steps thereafter. So I always say to my students that when it comes to mechanics, a lot of the time it's basically integration, right? Really messy integration. So you've got to be on top of your integration game to be able to do this topic. So when it's this proportional to velocity, so you can see there's no squares there on the two sort of velocity, horizontal and vertical velocities there. And basically we're gonna integrate to get our expressions for velocity and displacement from the initial acceleration stage. So let's start this. We're going to start with the horizontal and prove it. So what I'm going to do, let me just get rid of these arrows. I'm just going to copy this formula for us to sort of know what we want to prove. And I'll just pop that there. I'll crop just the horizontal to start off with. And let's start our proof. So I guess bear with me when we do this because it gets a bit tedious. The proof itself is lengthy, and a lot of the times I guess your teachers might ask you in an exam to they won't ask you to prove it, they'll just ask you to use it. So if that's the case, if they give you the formulas, then that's easy. But sometimes, and let's be honest, we don't know, and it's new to the syllabus. We don't know how the questions are going to develop, but if we do, if we are asked to prove it, then this is how you do it. So when we start with acceleration equals to k velocity, now we know we're going to basically prove velocity and displacement all as a function of t, because as for those that are once again on top of their 4-unit mechanics and integration game, we know that acceleration can be expressed in 3 ways. Okay? dv dt is the one we're going to use here, but obviously there's 2 other ways which we use for a lot of the other resisted motion questions. So, but the one we're going to use for this one here, because we want everything in terms of t, is dv. Now, instead of writing v, because it's horizontal, I'll write it as dt equals to k, negative k rather. Yep, it's negative because it's always against the motion, right, resistance. And then it becomes, in this particular instance, I'm going to basically collect my velocities and basically throw the dt over with the constant, and it becomes differential equations, right? Whereby I got 1 on x dot, sorry, equals minus k dt, and then I'm just going to integrate both sides, right? So obviously on this side it becomes ln. Yeah, remember you only need the plus c on one side because it's like the sum of all constants, so that one's negative kt plus a constant, right? And then now, because we're going to be finding 4 constants, let's call this C1, right? Ooh, something really important that I've forgotten. And that's when we do this, we always need to state our initial conditions, right? And that is absolutely crucial. So I'll put a little asterisk, initial conditions. In other words, what happens when t equals 0? Because when t equals 0, we sub in the values to get numbers or constants for us to use in our integration to find constants. So initially, let's assume, because we're assuming for this particular question that everything starts at the origin, right? Now, you can have elevation, etc. on certain questions for simplification for this series of formulae, let's assume when t equals 0, horizontally and vertically, it starts at the origin, right? So that's displacement initial conditions. And initially, we know that we have a vector of u meters per second, which we will then decompose into its vertical and horizontal, sorry, vertical, so that should be a y, and its horizontal components. Now, if that's initially projected at theta, then we know by Sokotoa that's going to be u sine theta, which we'll use, and that is u cos theta. So initially, we have these two conditions as well on the y and the x. So that is for velocity. Brilliant. So the reason why I'm going to say that is because right now we're going to use our first constant. So when t equals 0, we know that the initial velocity is u cos theta. So when you sub all that in, you get therefore. So let's see, I got u cos theta into here. Let me just check that. That's absolutely fine. So then we get C1 ln u cos theta equals to C1. Is that 0? Therefore, we have our velocity expression with the constant subbed in to be ln u cos theta. Now, if I have one eye on the formula I'm trying to prove, which is like, I see how it's exponential because they basically made velocity the subject, right? So basically, this guy here, I want to make that the subject. So I'm going to combine my ln's. So when I minus it over, it becomes division using my log laws, which is nice. So that equals to negative kt, exponential both sides because they're mutually inverse. Therefore, let's just skip a few steps. And then times a u cos theta up as well. E minus kt, beautiful. There you go. Now, normally, when we do without resistance, this step of getting x velocity or horizontal velocity is so easy. In this case, it's a bit more involved. Now, next step, let me see how much vertical space I have. Yep, that should, well, I should make a good start with that. So obviously, I replace that with a dx dt, right? To get my displacement expression. And then once again, I'm going to throw up the dt and then integrate both sides. So dt, integrate both sides there. Let's see what we get. We get x equals to, now u cos is constant and exponential with a negative k that becomes u, actually maybe I'll put a negative in front, u cos theta, the negative k, because I'm integrating, goes downstairs, and that's e negative kt, and then I add c2, which is nice. So if you get that expression there, once again, we're going to use our initial condition. Now, I wonder if I have any vertical. I do have vertical space, which I'm going to leverage. So I'm just going to pop this up here, if that's okay. Gives me a bit of space. Sorry, I just moved that. So I'm just going to do that. Okay, cool. Perfect. So let's do that now. So when t equals 0, I assume it's at the origin. So let's say this guy's 0, this guy's 0, so that's just 1. So it looks like C2, the constant is just going to be this fraction here, but thrown on the other side, so it's positive, which is nice. So when I sub this in, you can sort of see I can factorize it out and then get x equals to u. Let me see how I want it. Yep, perfect. U cos theta, okay. Let me just quickly scan upstairs to see the structure. See u cos k, perfect. And then factorize 1 minus e minus kt. There you go. Right, horizontal, not too bad, right? Not too bad. Just not pretty, right? Which is the key, right? The key, not pretty, but not too hard. A bit tedious, not too hard. There's my horizontal. So horizontal done. let's do the same now for vertical. So what I'm going to do, once again, I'm going to copy this, bring this here, uncrop the vertical part, just take the vertical part, and then I'm gonna do the same type of proof. So let's do this. I'm going to zoom in a bit, give myself a bit of neater piece of writing. So proof. So once we prove all this, let me do one question just to bring this to life a bit, and then that's our little short video for this. So we're going to start with the vertical gravity minus the resistance, right? Once again, we replace. So that's a given equation of motion for the acceleration, right? We're going to replace this guy with dv, or y dot dt. Yeah, so that gives us an expression there. Now, this one here is a bit more involved, but once again, use differential equations, group my expressions for velocity and move time over. So I'm just going to switch that over. So it becomes like -1. And don't mind if I factorize a negative out just to make my life that little bit easier. Let's have a look. So that's ky dy dot equals to dt, integrate both sides. And at this point, I might flip the equation around so I get t equals 2. Now that's linear. So that looks like an ln expression where I need k up front. So maybe I'll do a bit of manipulation here whereby, let's see, I need, well, if I factorize a negative out, I'll multiply that by k because I need that to do my ln, which means it's 1 on k here, right? And then the negative comes out. So I sort of get an expression that looks like -1 on k, right? When that comes out, ln, because the derivative now is upstairs of g plus k velocity plus c3, because I've already had 2 c's before this. Let me just see if the expression is fine. Yep, cool. Because now, subbing my initial conditions for vertical velocity when t equals 0, y dot equals to u sine theta. So I'm going to sub this guy 0, sub this guy into here. I sort of have like C3 as this whole expression on the other side, right? So C3 equals to +1 on k ln of g plus k u sine theta. Bit of a monster, but I'm going to sub that in. Therefore, t equals, now, when I sub it in, smart idea, see how it's 1 on k, both of them? I'm going to have a quick gander. See how that's negative k? I have a feeling I want to factorize out -1 on k. So when I throw this guy over the fence, I'm going to get that negative kt action that I need for y dot. So just letting you know, that's what I'm playing. So when you subtract 2 ln's, obviously it's division. I always have one eye on the thing you want to prove, just in case your algebra gets a bit more complicated if you don't, right? So let me just see. It looks to be almost there, because then I'm going to times that perfectly. Just to give you a vision of what you have to prove, right? Or what I'm saying there is that I want a negative kt, right? So when I times this up and then I exponential, I'll get negative there. So that's why I factorize -1 on k and not positive. Secondly, you can see the bracket there, g plus that's going to be this guy multiplied up, minus g divided by k. So I have it, right? Now it's just a simple case of algebra. So once I get that, let's make this the subject. So like I said, exponential both sides, or times it up and exponential, you get kt equals to g plus ky dot on g plus ku sine theta times this expression up. You know what, let's just be heroes and just conclude. Okay? I don't think that requires too much. I'm sure your teachers will be happy with you just to go, therefore times up minus divide by k, beautiful, right? So 1 on k, g plus ku sine theta multiplied by that e expression, and then minus gravity. So monster, but not too bad, right? Tedious, but not extremely difficult. Yep. So that's how you prove that. And then lastly, let's prove the displacement. So I'm going to have to integrate this guy. So what I'm going to do, because it's a bit of a monster, and I probably will take a few more steps than I probably would have right now. I'd like to get it downstairs. So I wonder if I can let me just ungroup this. Let me just copy this expression. Stairs here, and then start my work sort of up here. All right. Delete that, perfect. So using that velocity expression, let me replace this with dy dt, and then we go again. So I need to integrate. It's a bit of a monster right now, but it looks pretty good. It's just that there's a lot of constants, and that's absolutely fine, right? So everything that's constant, that's constant. That's constant. And that's constant. So the only sort of variable here is t here, which is an exponential. So really easy to integrate. So if I wanted to get rid of a dt there, put a dt here, integrate both sides, I get my y displacement equals to, now factorize obviously 1 on k out. Integrate this whole thing, that's constant. So it basically just becomes a fraction where negative k sort of goes downstairs, e negative k, k, t minus integrating this guy, it's just gt, and then plus c4, right? So initial conditions when t equals 0, y equals 0, assuming that it starts on the floor, and then c4 now, you can sort of see that's 0. This is 0, so that becomes 1, that's 0, that's gone. So this fraction is the only thing that stands. So you sort of get like minus 1 on k squared and this numerator, which goes on the other side. So it looks like it's going to be a positive g plus ku sine theta on k squared. I think that's right. Let me have a quick gander at what I need to prove. You can see the k squared, perfect. And that's the 1, that's minus, that's a negative, minus gt. Okay, perfect. Perfect. So let's sub in C4 and you get an expression. Now I'm going to use rainbows to expand this and this. So I sort of get like an expression that looks like g plus ku sine theta on, well, let's put a negative in front, k squared e of kt minus gt on k plus my newfound constant on k squared, and then I'm just going to do the final step of factorizing. That's a minus, that guy's the same, so it'd be like, now let me just look at how they express that. I think I put the fraction first. Yes, perfect. Fraction first, so big fraction there, k plus ku, sorry, g plus rather sine theta on k squared multiplied by 1 minus e minus kt minus gt on k squared. Guys, that was a bit tedious, and it took about 20 minutes to prove. Hopefully in a test you don't have to prove all those elements, but if you do, not too bad. So that basically summarizes the 6 equations of motion that we need for with resistance proportional to velocity. So now I'm just going to do a quick question which I sort of prepared in advance that utilizes this information. So in this question, let's just once again trawl through the English and then comb through the English and then pull out the relevant mass related formulae. So a 1 kilo object, right? That's good because when I equate forces, it's MA. 1 is nice because then it just becomes A. Projected 45 degrees to the ground, velocity of that. Yeah, the gravity is 10, that's nice and rounded. Proportion, and this is absolutely proportional to the object's velocity. Next lesson, I'm going to do proportional to the object's velocity or square velocity, right? And k is 0.01. So the classic questions determine this. Now, I'm going to say something quite important. So you'll see that determine that. Verify the object's total time of flight. Now, when you do these questions, and I'll refer back to the initial question, the initial formula here. When you have, actually, let me zoom out to explain this. When you have without resistance questions, you can find the total time of flight by setting this to be 0. Yeah, because it lands back on the ground, and then you solve a quadratic, right? That's pretty easy. However, when there's resistance, can you imagine setting this to 0 and trying to solve an equation for t where there's an exponential function in the same sort of equation as linear, right? Almost, we can't solve it, right? The techniques we have at play can't solve it. So what you'll find is that when you have questions that ask for total time of flight with resistance, they don't ask you to find the total time of flight. They basically ask you to verify it. In other words, they give you the answer, and all you have to do is just sub it in, right? So it changes the type of questions you'll get for this type. So you'll see that in most, if not all, questions with resistance, verify that, and they give you the time. So you just sub that in and check that the y value is 0, so it lands on the ground. And then using that total time of flight, we can find horizontal range, and max height is unchanged in terms of approach. So, right, what I'm going to do, just to shortcut our process, I'm just going to borrow these formulae. Actually, no, I can't borrow. I'll just leave it there for comparison's sake, right? So let's do this. So for part A, horizontally. I'm just going to zoom in if that's okay. So we know that horizontally it's proportional. So maybe before I begin horizontally and the like, let me set up my initial conditions as well, and maybe a quick diagram. So obviously it's a sort of not symmetrical parabola. So initial velocity there is 16√2 at an angle of 45 degrees, which is nice and exact. And mass is 1 kilogram. That's important. So when t equals 0, so initial conditions, I've got x equal to 0, y equals 0, starts on the floor, right, initially projected from the ground. And then for u of x, right, so that's 16√2 times cos 45. Now we know cos 45 is 1/√2, so that's just 16, perfect. And what, exactly the same number, right? Because of 45, it's 1/√2 again, so 16. 16 and 16, that's nice. We're going to get some whole numbers, right? Brilliant. Right, so hopefully this derivation of numbers is going to be quite quick with nice whole numbers. And also, last but not least, gravity is 10, right? Brilliant. Let's do this. So initially, horizontal acceleration only has resistance at play and is proportional to k. Oh, sorry, I should really write in my diagram as well. So in k equals to 0.01 or 1 over 100. Maybe I'll do 1 over, no, with a 0.01. This makes it a bit easier. So it's always k times velocity. 1 down, 1 equation down, 5 to go, right? All right, let's move a bit more pace. So dv dt equals to negative 0.01. That, use my differential equation, switch it around. Now, when I divide by that, it'll be, actually, I'll leave it up there. So it becomes like 1 on x dot dv dt, integrate both sides. And I get ln of this guy equals to negative 0.01 t plus c1. Yeah, subbing my initial conditions. So when t is 0, initial velocity is 16. So sub 16 there, that's gone. So c1 equals to ln of 16. So, oops, I've got no more vertical space. That's an issue. big issue. Probably don't need that much anyway. So, guys, if you're happy for me to sub that in and then basically make it subject, I sort of get like x dot equals 2. So I'm just gonna cheat a little if that's okay. So if you sort of picture that's ln 16 minus it over, so it divides. So then I e times the 16 up, so you should get 16 e negative 0.01 t if and when you make velocity the subject. 2 equations down. Let's see. Let's verify that's perfect. So I'm going to replace that velocity now to find displacement with dx dt equals to 16e01t integrate. So move this guy over here, integrate both sides, and I get x equals to 16. That's e minus 0.01t divided by negative 0.01 plus c, is that c2? Now let's clean up this, clean this up a bit. So x equals to that divided by 1, so it actually multiplies by 100, so negative 1600 t plus c2. Right, when t equals 0, initial conditions is that it's on the origin, at the origin, then c2, now that's 0, that's 0 equals to positive 1600. Sub that in and I get an expression, factorize it as well. 1600 1 minus e minus 0.01 t. So everything sort of falls into place, and it's so nice when the nice exact values are there, right? And using gravity of 10 as well. So you can see structurally exactly the same. I've just got some nicer constants, so there's less fractions involved. So horizontally done. Now let's do a slightly more complicated version of vertically. So vertically, it's a bit more complicated because it begins with gravity working against you, but also your resistance of K. Oh, sorry, that's not. Let's use 10 minus 0.01. What's it? All right. So replace this with dv dt. Maybe factorize a 10 out. Sorry, negative out rather. Oops. And then switch this around. So I'm gonna basically bring these guys together. Maybe leave the negative there for the dt. Doesn't matter where you put the negative, it's just negative anyway. So I sort of get like 1 on 10 plus 0.01 y dot dy dot, so negative dt. Integrate both sides. That is ln, so I need the 0. Sorry, maybe I'll have to times by 0.01, which means I divide by 0.01, which is 100. So it becomes like 100 ln 10 plus 0.01 y dot equals to negative t plus c3. So use my initial conditions. Let me just check that 100 is perfect. When t equals 0, y dot equals to 16. So let's see, that's 0, that's 16. 0.01 times 16 is 1.6. Is it 1.6? No, 0.16. So you actually get C3 equals to 100 ln of 10.16. Just check that, 10.16. Weird, right? So sub that in. Now what am I trying to do? I'm going to move the ln's over, combining. So can you imagine when I sub this into here, move it over, I sort of get like 100 ln of 10 plus 0.01 y dot all over 10.16. So minus t. So what I'm going to do, divide the 100 over, so it becomes 0.01, and then so I'm trying to make this expression the subject. So I'm going to skip a few steps if that's okay. So basically, once you get that divided over exponential, times it up, minus 10 divided. So it becomes 100 because it's 1 on this guy, divided by 10.16 exponential to negative 0.01 t minus gravity. Let me just check that. That looks perfect. That looks perfect. So that forms my velocity for y. Yep, let me just look at the structure compared to this. 1k, beautiful, g, yes. She's like, that's a constant, perfect. All right, cool. You know what, at this point, I probably don't need this anymore. Or maybe I'll just throw it over to the right, because I need vertical space more. Let's move that up. Get rid of this line. All right, let's keep going. All right, it's a bit long-winded, and I apologize, right? So, but you know, I think it's good to have, for you to have some theory on this. I don't know whether this is covered in this depth at school. Maybe they'll just give you the formulas, don't know now. So before I do this, I'm going to integrate. I'm going to expand that. And just like I said before, that's a constant. This guy here is, actually, I won't even, no, I'll leave it factorized. So let's just integrate. So I'm just going to, once again, populate this down here. You can expand, it's up to you. Might be nicer actually. So when I get rid of this, put the dt here, integrate both sides. So on this side becomes y, this 100 comes out. So that there becomes 10.16 e minus 1t divided by negative 0.01. That's a constant, 10t plus our last constant there. Almost there, guys, almost there. When t equals 0, I know y equals 0, starts on the ground. That's gone. So I got C4 equals that 0. So that's negative. So remember, that's also 100. So it'll be 100 squared. Which is 10,000 times that's 100, 100,000, 101. Okay. So it's like 101, 600. 600. That's a constant, is it? Yes. Yes. Therefore, so now if you were to use rainbows to expand, oops, sorry, no, I wanted a green pen. To expand this and this, get your final result to look something where 101, 600, 101, 600 factorizes. And then it'll be 1 minus, because it would be the constant, minus this e expression of e minus 0.01 t, and then minus 1,000 t. All right. Oops. Bump that up. And guys, that's our 6 equations of motion. So I guess, you know, it's not that hard. It's massively tedious, right? Massively tedious, but not too bad, right? There it is. It's got the same structure, perfect. Right, so if you got that right, you should be able to do BCD without that much of a challenge. So what I'm going to do, let's just copy down this question, and I'll probably need actually the last derived expression for. That's awkward. Yeah, I'm good at that. I need to borrow just the expression. Thank you. Need that expression up here. Perfect. All right, guys. So, whew, part A done, right? Now, part B. Oops. This is going to fly, right? So this is going to be quick. Part B. So part B is really easy. We need to verify that t equals to 3.183 is the total time of flight. Now, we know that for total time of flight, right, y equals 0 because it lands on the ground. Yeah, so for this one, when y, oops, black pen, when y equals 0, right, I want to verify that this guy is in there. So what I'm going to do actually, I'm going to go left-hand side equals to 0, yep. And the right-hand side equals to 101,600, 1 minus E minus 0.01 T minus 1000 T. Oh, sorry, I didn't want T, you know, I want to actually physically sub in 3.183 minus 3.183 on your calculator, right? If you do punch that in, you should get a number, and you can verify this to yourself, that looks approximately to 0. Therefore, right, since the left equals to the right, or approximately equals to the right, you can conclude, therefore, time of flight is approximately 3.183 seconds. Now, there is a question, and I'll do this in sort of lesson 3, where we compare the times of flight, or the total horizontal ranges across no resistance with resistance, proportion to velocity, and then proportion to velocity squared. So it's actually quite cool to see the 3 side by side. Okay, cool. Let's do part C. Now, very easy. Total time of flight. Total horizontal range. I found the time of flight. Sub this into the x expression, right? So once again, let's go back and borrow some formulas. Right, where's my expression for horizontal? There it is. Perfect. Borrow this and slap it up here. And all I'm going to do is just sub in. So sub in t equals to 3.183, because that would be my total time of flight. Right. So x equals to 1600, 1 minus e minus 0.01 times 3.183. Right, you punch that in your calculator and you will get 50.126 meters. Now, that's my rounding actually. I think it's 1 dp. 1 dp. Yeah, I've done too much. That's better. So pretty straightforward. Now, max height. Whenever we do max height, we basically do what we always have done, where at max height, vertical velocity is 0. So what I'm going to do, find the time taken to reach max height, and then sum that time into the y expression. So once again, let's borrow an expression. Where's my, here it is. This guy here is groups. I'm going to ungroup that. I love being able to borrow formulas and learn from previous slides, so it saves me a bit of time of writing it down over and over. So paste that formula in here. So for max height, we're going to set vertical velocity to 0. So for max height, vertical velocity is 0. So when I solve this equation, so this one I can solve, right? While the ones where I couldn't solve, it asked me to verify. This one here, I can solve that equal to 0. So chuck the 100's gone. 10 over. So you can sort of make t equal to, if you sort of really make it the subject, actually 100, it'll be ln of, what was it, 10 on 10.16. I believe you punch that into your calculator and you should get time. Actually, you know what? Save that expression. Save that expression because I want it, well, nice and exact if that's possible. And then I'm going to sub that into y. Yep. So sub this into this expression, and you should get from your calculator y equals to 12.7 meters. So nothing too wow for questions B, C, D, but it's just intense for question A. So that is projectile motions with resistance proportional to velocity. Next lesson, I'll do proportional to velocity squared. And the third one, let's do a few past paper questions if we can, from some of the schools that have dared to put questions in for the first year of their trial papers. So hopefully that was useful. I'll see if you like that lesson, please give me a like, give me a subscribe. I'll see you at the next lesson. Thank you.